Well, welcome everyone to this week's meeting of the Space and Time After Quantum Gravity project. This week I'm very happy to present Paul Sanders, who comes to us from the Institute of Theoretical Physics at the University of Leipzig, where he is a postdoc. Paul did his PhD in 2009 at the University of York under the supervision of Chris Fuster, and had postdoc positions in a number of places between then and now. He mainly works on quantum field theory and curved spacetime and in black hole thermodynamics. And of course, the reason why he's here is because he's won last year's essay competition, one of 3 prize-winning essays on the Space and Time After Quantum Gravity project. So please, Paul Sanders, what can mathematical categories tell us about spacetime?
Yes, thank you very much. It's a great pleasure for me to be here in Geneva for the first time. So let me start by thanking the people who have made that possible. First of all, the organizers of the essay contest, so Nick Huggett in Chicago and Chris Wittrich here. And of course, the referees of the contest for all of their very helpful constructive criticisms. Perhaps a slightly more surprising thank you goes to a practical philosopher who was actually the first one to point out to me that there is this context. So that was Rebecca Gersbach. After I heard about this contest, it didn't actually take me long to come up with a topic that I would like to write about and to explain. It has to do with quantum field theory and curved spacetime and with categories. And basically already in my PhD I had some ideas about why these categories were being used there. So I'd like to explain all of that to you in a moment. Before I get to that, there is one other thought that I would like to share with you. So even after I had decided what I could write about for this essay contest, I was still hesitant to actually write it and submit an essay, basically for 2 reasons. The one is that I am not very well trained as a philosopher. I've had some basic courses on philosophy of physics, but not very much. So I was a bit hesitant whether I would actually be able to successfully communicate some of the ideas coming from my area, mathematical physics, into the philosophical community. And the other reason is that I was a little bit hesitant because of the reputation that philosophy of physics sometimes has within the physics community. Don't be offended, it's not actually as bad as it sounds. In my community, people actually are aware that philosophers use different methods, they ask different questions, and that's perfectly legitimate. Nevertheless, I know that there are some physicists who would argue that philosophy of physics is completely useless, and they would even reduce it to this caricature that, a philosopher will only admire a problem, but a physicist will solve it. I don't know any people who really hold that position, so it's fine from that point of view. But still, I do know a number of people who hold this view that whatever happens, whatever problem you encounter, philosophy comes last. Physicists will work on it, they will do some mathematics, they will work on it, solve it, and then after the physicists are done, philosophers can come in and say whatever they want to say about it. For the physicist, it often doesn't even matter anymore because the problem is solved. And I have always found that rather disappointing. So that almost made me doubt whether there was any real use of writing this essay and trying to communicate to the philosophical community. So what convinced me there was actually a very interesting lecture that I heard by a philosopher, James Conant, who was talking about problems and puzzles in the philosophy of Thomas Kuhn. And he had a very nice, very general story, but from my perspective, I was only hearing more or less the things that are relevant for my context. So I pretty much heard him say that quantum gravity is a real problem because we don't even know what really counts as a solution, and perhaps we don't even have the right concepts to formulate the question. I also felt that I heard him say philosophers of physics are exactly good at those kind of problems, and they don't necessarily need to wait for the physicists to do something. They can be proactive about it and go in there right away. The other thing that I thought I heard him say is that physicists should actually jump in as well and be more happy to communicate with philosophers. So that's what convinced me to actually write this thing and send it in to the philosophers and see how it would be received. So that's also one of the reasons why I'm now actually here telling you about what categories can say about space-time. And when I say categories, I will always mean that in a mathematical sense. Okay. Is this thing pointed up? Yeah. So the outline of my talk is basically to start with a bit of motivation of why this is an interesting question. Then in point 2, I will spend some time explaining the basics of my background, so quantum field theory and curved spacetime, in a particular axiomatic framework which uses these categories. And in case you don't know what a category is, I will give a brief review of that as well. And I will conclude there with 2 notes on how locality already appears there in an interesting way, although at that level it might still be a bit puzzling. So in point 3, I will give a bit wider and more precise analysis of what categories are doing in this formulation, in this theory, and what they have to say about space-time. And then I hope to get around to a view to quantum gravity, things that we could learn that may be relevant there, and some conclusions and an outlook. So, first of all, the motivation. So I'm going to start here with something which I hope is not controversial, that if you look at classical general relativity, we think we know what a space-time is. Every textbook basically will tell us space-time is modeled as a Lorentzian manifold, so a manifold with a Lorentzian metric. And then possibly some additional assumptions in there, like smoothness, dimension 4, orientable, time orientable, often also globally hyperbolic, so we can have nice initial value formulations for normally hyperbolic field equations on the manifold. When we go towards quantum theory, this notion of space-time becomes a bit problematic. This is a well-known argument. So operationally, if we want to determine a space-time point, very precisely, we would need to have higher and higher energies in smaller and smaller regions. And the basic argument is that at some point you will get a gravitational collapse and you can't measure anything anymore. At least you will not be able to reproduce the measurement because there's going to be a black hole. So what people say is that space-time breaks down at the Planck length scale. And that's a basic problem for certainly quantum theories of gravity, because they would like to give a valid theory even at such length scales. So that's something you would have to deal with. So the challenge for quantum gravity, at least one way of formulating it, is how does this space-time somehow arise? So for a given quantum gravity theory, suppose your friend comes to you and says, I've got this nice theory here. You can ask, how does space-time arise there as an approximate concept in this particular case? So that's an interesting question to do. As a philosopher, you might also be interested in a slightly more general question and say, well, I may have 5 different friends with 5 different theories of quantum gravity, or perhaps even more than that. So quite generally, what would be required of a quantum theory of gravity to really claim that it explains space-time as an approximate concept? So here you can really only use some general properties of the theory and perhaps general properties of space-time. And I guess at that point, at the latest, you ought to wonder as well, so what is this space-time anyway? Is it really best modeled as some Lorentzian manifold, and what are its symmetries? And I'm going to try and give a slightly different perspective than that Lorentzian manifold in this talk. So in this presentation, I'm basically going to take the point of view of quantum field theory in curved spacetime in this axiomatic framework of locally covariant QFT, and I'm going to consider how spacetime occurs there. So this axiomatic framework basically encompasses some of the most precise theories that we have. You can basically do the entire standard model in some given background gravitational field, and that's quite a bit. What we do not normally do is to include the dynamics of the gravitational field. That seems to be a little bit beyond the mathematics that we can do. So the interesting point for me is going to be that this framework uses the language of category theory and I'm going to try and convince you that that's not really an accident. So let me first tell you a bit more about what this framework is, what categories are, and how they appear in the formalism there. So the category, I'm going to use this kind of script and abbreviate them. So cat would be a case of a category. Basically consists of two things. There's a collection of objects in there, and there's a collection of morphisms or arrows between the objects. So you can nicely depict them graphically like that. And they should satisfy a certain number of axioms. So each morphism has a source and a target, so it's a nice arrow. When the target of one morphism corresponds to the source of the next one, you can compose them. So there's a composition rule of morphisms. And then the composition should be associative. Each object should have an identity morphism satisfying these obvious relations. So that's what a category is. Very often it's useful to think of categories as sets with certain additional structure, and the morphisms are then maps which preserve that structure, but you can also take a more abstract point of view on that if you want. Another thing that I'm going to need quite a bit is a thing called covariant functor, which is a mapping from category 1 to a category 2. Basically what it does, it maps objects to objects, and it maps morphisms to morphisms. And of course, in such a way that when I've got a morphism from A to B, then f of f, so the map morphism would be from f of A to f of B, and it should preserve identity morphisms, and it should preserve the composition of morphisms, so it preserves the structure of the category. So that's an overview of the general definition of a category. I'm going to introduce two examples. They are not the most typical examples, but they are the most relevant examples for my talk. So the first category is category of localization regions, where as objects I'm going to choose four-dimensional globally hyperbolic Lorentzian manifolds. So that means I'm going to choose a four-dimensional manifold, Lorentzian metric on that, making the manifold globally hyperbolic, and I will probably want to include an orientation and time orientation, although if you want to leave that out, it's also fine by me. Morphisms are going to be embeddings between such manifolds. So I've depicted one of those things here. And they should be such that they preserve the metric, they preserve the causal structure, they preserve time orientation and orientation. So they basically just preserve the structure that we have. So that's one category that's going to figure in this talk a bit. The other category has to do with quantum physics. So for the purposes of this talk, a quantum system is going to be described by a C-star algebra of operations that I can perform on the system, and together with a set of algebraic states that I'm going to allow in the system, where a state in this setting is a linear expectation functional, so it should be something that is normalized and that should be positive in this algebraic way. And together I then have operations, which includes my observables, states, which gives me expectation values for that, so I can start making predictions and measuring things. In case you're more used to quantum theory in terms of a Hilbert space, I would like to tell you that any algebraic state actually yields a Hilbert space and a representation of the algebra on that Hilbert space, and some vector in there that actually represents the state in the usual way. So in a sense, Hilbert spaces come for free. I'm not taking them as the basic object, but the algebras and the states instead. So that's not a category yet, but you can put these things in a category if you like to. So the category that is often used in my area of research is what I'm going to call alg here for algebras. So objects are C-star algebras with a unit operator in there, and the morphisms, well, we often take them injective, although that's perhaps debatable, but certainly unit-preserving C-star algebra homomorphisms, so they preserve all the structure of the algebra, products, linear combinations, and things like that. Okay. So that's what categories are and some of the basic examples of them that I'm going to need in this talk. Now we come to the question, what is a locally covariant quantum field theory? So the axiomatic framework that we use, that was written down by Brunetti, Freydenhauer, and Ver in 2003, says a locally covariant quantum field theory is nothing else than a covariant functor from this category of localization regions to this category of algebras. So to each localization region, I assign an algebra of operations that I can perform there, and to each embedding of localization regions, I basically want to assign an embedding of these algebras. On top of that, I probably want to impose some axioms on this functor so that it behaves in a nice way. So I'm listing two examples here. One would be the time slice property, which tells you that there is a nice causal dynamics in your theory. So when I embed one smaller region of space-time into a bigger one, but such that the smaller one actually already contains a Cauchy surface, that is initial data surface in the bigger manifold, then I should be able to know everything that will happen in the entire manifold. I know the Cauchy surface, so I know enough. So such a morphism in the category of localization regions should be mapped to an isomorphism between the algebras of the two spacetimes I'm looking at. Another rather intuitive axiom that you can impose is this causality axiom, where you say if I've got two morphisms with the same target manifold, and if the images are actually space-like separated, then the corresponding algebras should be commuting algebras within the algebra of the entire space-time. There are more axioms that you can impose, and that would be natural to impose, but I'm not going to list an entire list of them. So this framework is actually also very flexible. So I've given you a basic version, but there are actually variations of it already in the literature, which are also very useful. So you can include more background structure in the category of localization regions. You could say, you could be looking at electromagnetism perhaps with an external source. This source I'm not going to treat as a dynamical object, so it's part of the background structure. You can include that in your category if you like. Similarly, if you want to describe fermions, you can include a spin structure or something like that. So that would be on the side of the localization regions. You can do something similar on the side of the algebras and say, well, on top of just algebras, I might want to include also a selection of states that I'm going to allow, because some of them might be badly behaved. Or maybe you don't like the algebras at all and you want a completely different description of physics. In principle, you can do quite a bit. So finally, to list a few examples that we can do, free fields, we can certainly manage those, but also the entire standard model and perturbative quantum field theory can basically be treated in a generally covariant setting with technical modifications which are very similar to what you would do in a Minkowski space. So we do not lose any physics by extending this to a curved space-time setting. In fact, we do gain some new physics, of course, because things like the Hawking radiation phenomena can now nicely be described in this setting. Okay. I promised you two examples of how locality already figures in this rather basic framework in an interesting way. The first one has to do with states. So here I'm actually going to look at the situation where instead of just algebras, I'm going to use a category which I will call sys for systems, where an object corresponds to an algebra of operations together with a set of allowed states. And the morphism corresponds to, well, a morphism between algebras in the same way that we would normally do, but also such that if I've got an allowed state on system 2, and I compute the pullback of that, so this is a definition for pullback, and we'll give you a state in system 1. The state that I get in that way should then be an allowed state in system 1. So this pullback should define a map from S2 into S1. So one way of stating that is that a state in S1, so an allowed state on the algebra A1, can be extended to some state on A2 on S2, so it's an allowed state, if and only if we have this pullback relation. Now, what does that have to do with locality? Well, there have been some arguments saying that we should actually impose a condition in this setting that has to do with these states. So the condition is called local physical equivalence. It says if I've got some system on some Lorentzian manifold A1, every state I can choose there should be extendable to some state on a larger Lorentzian manifold for every embedding that I have there. Now, why would you want to impose that condition? The motivation is as follows, and this is very interesting. If I've got a state on the smaller Lorentzian manifold that can be extended to some larger manifolds, but not to others, then basically my state contains information about what the manifold looks like outside of the region that I'm actually looking at. So in a sense, it contains information that a state should not contain. So this axiom that we're formulating here basically disallows that and really says states should not contain information about the manifold outside of the region of interest. I'm making a somewhat technically simplified formulation of this axiom here. In the cases that we know, you would actually have to use some topological arguments and say almost every state and things like that, but I don't want to go into that. The second example that I would like to talk about has to do with the notion of doing the same physics in all space-times. Intuitively, it seems very obvious that if you look at this example, free scalar field on a Minkowski space satisfying this Klein-Gordon equation should basically describe the same physics as a free scalar field on a Friedmann and Robertson-Walker space-time satisfying the same equation, except that now this box is basically the D'Alembert operator on a different space-time, so the metric comes in there. The idea is that it's the same field, same equation, it's just somehow boundary conditions, background things that we have modified. Now, Schuster and Verg basically asked the question in a very general setting. When we've got one of these axiomatic, locally covariant QFTs, how do we know that that describes the same physics in all space-times? And they found that that was not really obvious. So what they needed to use is a notion of equivalence between theories. So this is a very general categorical notion again. When I've got two functors, there is a notion of natural isomorphism between them, which is written in this way. So perhaps the easiest thing to do is to look at the picture and think about what happens. When I've got some Lorentzian manifold and two theories, they will map that into two algebras. And I would like to have some isomorphism between these two algebras in the category of algebras. That would be the statement that, at least on that Lorentzian manifold, I get the same theory, or at least an isomorphic theory. On top of that, for a natural isomorphism, you need to do more. You need to say, this equivalence here ought to be compatible with the morphisms in my categories. So when I do the same thing on some other object, and in the background here I've got some morphism from M1 to M2, I should be able to say, if I go from this A description to my B description, which is isomorphic, and then embed that into the B theory on the larger M, that would be exactly the same thing as if I take my A description, first embed that into the A description on the larger M, and then use my equivalence there. So this diagram should be a commuting diagram. That's the notion of natural isomorphism, and that would be a good statement of saying that two theories are equivalent theories. Now, Schuster and Verg then had the following idea. If we want to say that locally covariant quantum field theories really describe the same physics in all space-times, then the following should certainly be the case. When I've got two of these theories, and I know they're isomorphic on one space-time region, then they should be isomorphic on all space-time regions, so there should be a natural isomorphism between them. I mean, they all both describe the same physics in all space-times. They, in a sense, also describe the same physics on a fixed space-time, so A and B ought to be really the same everywhere. And interestingly, Schuster and Verg then proved the basic axioms for locally covariant quantum field theory that were being used at the time are not enough for that. they also introduced an extra axiom called dynamical locality that actually does imply this same physics in all spacetimes property. I'm not going to go into the details of that precise condition. You can look it up in their paper if you're interested. Just wanted to say that this analysis makes extensive use of the structure of this category of localization regions and of making variations in the background metric. So I feel that this is an interesting result and also an interesting thing to mention to philosophers, because it seems to have an interesting parallel in philosophy that goes back quite a while. It seems to be related to the question, how do we identify objects even though circumstances might be changing? How do I know that the orange in the tree is the same orange that is lying somewhere on the table later on? Instead of identifying objects, the question is here, how do I identify field theories? But in both cases, you could argue that space-time seems to be playing a role in there, although the role that it plays is also very different again. So it's an interesting parallel. I'm not entirely sure what to make of it, but it seems to be very interesting. Okay, so that's all that I wanted to tell you about the basics of locally covariant quantum field theory and some initial ideas of how locality figures in there. And now I want to continue and delve a little bit more into the use of categories in this setting and what that tells us about space-time. So the basic question is, why do these locally covariant quantum field theories use categories at all? So we can ask that question in a very general setting where on the right-hand side, I don't even care very much what category you choose there to describe the physics side. What I'm going to argue, nevertheless, is that the use of a category at all already encodes a certain systems view of the world, and it sort of gives you a kind of model theory from modal logic that describes very nicely an operational perspective to what we do when we do physics. Secondly, the use of this category of localization regions was introduced. It was introduced to encode locality and general covariance, and combining those two with a functor basically provides a somewhat different perspective on the notion of space-time. So because of these connections which go a bit deeper, I think the use of categories is more than just a bookkeeping device. It actually connects to things like systems view of the world and the notion of space-time. Okay, so let me give some arguments in a bit more detail, starting with this category phys. So the use of that category may be interpreted as follows. We could say that a physical theory is basically given by the systems that it can describe, and morphisms in this category phys basically, well, they have to satisfy some basic relations as a definition of a category. You can view these relations as codifying a notion of subsystems. So we are saying this system is part of another system. So the use of a category there is actually quite general, and you might already think of that even before you start wondering about space-time or something like that. Physical theory has systems and subsystems. That's a very general point of view. So another way perhaps of saying that is that the morphism between two objects of this category would mean that subsystem 1 describes less degrees of freedom than subsystem 2. So in this very general setting, I guess you can also wonder what kind of physically motivated conditions should I impose on this category phys. I'm not going to address that at all, but you may come up with a number of things perhaps that restrict that. So on top of just this systems point of view, I also want to make a connection to modal logic. Now, perhaps you know modal logic more or less from a possible worlds point of view. I want to take a slightly different view on that. I want to use the possibility semantics. So a possibility there is an incomplete description of circumstances. So it doesn't specify everything exactly, but it specifies some things, and that is enough to at least give truth values to some logical sentences, perhaps not all of them. What people then do in this possibility semantics is to use refinements, which basically extends the set of circumstances that you're specifying so that you get truth values for a larger set of logical sentences. The connection to this category phys may now be fairly obvious. Every object basically corresponds to a possibility. So the circumstances we are specifying are basically the things we can measure in the system, the states that the system can be in, things like boundary conditions as well. You can then also say that if I choose a specific state that my system is in, that would specify further circumstances. If I have time, I hope to address that towards the end of my talk. Morphisms in the category would correspond to refinements. You're going to a larger system, so you're specifying more operations that you can perform, and you basically know more. This point of view, the system's point of view, and the modal logic appearing in this way exactly corresponds to what we normally do in the lab, or what we would like to do. If we are in the lab, we are making a prediction, we want to measure something, we don't really want to specify conditions or circumstances for the entire universe in order to make a prediction. It's enough to specify circumstances in the lab or in nearby region. So that's all I wanted to say about the side of the category phys. Now I'm going to come to the category of localization regions. So there's one interesting analogy that I would like to make to motivate the use of this category. And I want to focus on the question, what do we do when we compute some local quantity, for example, curvature in general relativity? So there's one part that seems to be fairly broadly appreciated. If we want to compute local curvature, we choose some choice of coordinates, we express everything in those coordinates, do our computations, and we get a result out that is the local curvature. And it's, I guess, the miracle of general relativity that it doesn't matter which coordinates you choose, the curvature you get out is independent of that. So the reason why we use differential geometry in general relativity is to get a nice coordinate-independent language to express those kind of computations. Now, there is a completely analogous argument to be made saying that if I want to compute my curvature locally, I don't need to know what my Lorentzian manifold looks like far away. I need to know it perhaps in a small region, but I can extend it whatever way I like. Now, choosing some Lorentzian manifold is very much like choosing some choice of what the entire universe would look like, and you don't really need to do that. So I would argue that using this category of localization regions is a tool to basically remove any prejudice on what the entire universe looks like and to really focus on things that are happening locally. So in that sense, using this category of localization regions is very analogous to using differential geometry in general relativity. And I think that the use of that category is perfectly consistent with the basic motivations of general relativity.
Sorry, quick question then.
Yes.
So is log sort of maximal in some sense then? It's got every way of extending or something?
That is a somewhat tricky question. I'm not entirely sure how to answer that. Perhaps the two comments I want to make address that to some extent. So let me first make these two comments and then you can say if you want to ask the question again. So the first comment I want to make is that the category log certainly contains very many Lorentzian manifolds, and it's enough to do interesting physics. The second comment is that there have been some attempts to actually extend that further to a larger category, in particular by Bernard Kay, who introduced the notion of F-locality. And there it turned out to be very hard to actually get any theories. So if you can't even do a free scalar field in a larger category, then it's perhaps wise to give up hope of doing that. Now, it's quite true that this category that we're using still, it doesn't give, it gets rid of the prejudice of choosing a particular choice of a universe, but it still includes some prejudices. So we still use Lorentzian manifolds which are globally hyperbolic oriented, time oriented, and you could argue, well, do we really need those properties? Do we want to get rid of those as well? It's an interesting question. I guess I would be open-minded about that question. So if you can extend it to a different category, get rid of some of these assumptions, that would be interesting, and I would be very willing to discuss that. But for the moment, being very pragmatic, this category is not a bad choice because we can do a lot of interesting physics with it, and it seems to be pretty well motivated, getting rid of at least a lot of the prejudice that you would have when you fix one Lorentzian manifold. Does that answer the question?
Yeah, I think I didn't quite understand when you defined Locke, that it sort of means all four-dimensional globally hyperbolic spacetimes or something like that.
Yes.
Yeah. Okay.
So that's the idea, that it does include all of these satisfying the properties that we listed.
Got it.
Okay. So this is more or less the motivation why we use this category. This is not actually the motivation why it was first introduced. So let me get to that as well. It was introduced because the morphisms of this category encode exactly two basic principles, general covariance and locality. So for the general covariance, you could basically look at the diffeomorphism between two manifolds, to transport geometric and all other structure like orientation, time orientation. That gives rise to isomorphisms in this category. So all of these things are in there. Similarly for locality, if you look at a suitable region inside a larger Lorentzian manifold, you can have a canonical inclusion, and that also gives rise to morphisms in this category. On top of that, you can say that a general morphism can actually be decomposed in terms of these two things, just by saying, when I've got a general morphism psi, I basically just map my source manifold onto its image, which is a diffeomorphism, and then I use a canonical embedding of that into the target manifold M2. So general covariance, locality are in there, and that's basically all that is in there in some sense. So what we're doing here is, in some sense, extending the symmetries of general relativity. Normally people would say the symmetries in general relativity are the diffeomorphism group on some Lorentzian manifold. Now, if a Lorentzian manifold really is just a prejudice of what the universe would look like, and you don't want to be prejudiced, you would like to get rid of that. Basically, this category Locke extends the symmetry group on any one Lorentzian manifold to a kind of symmetry category on general relativity, treating general covariance and locality on an equal footing and saying that locality deserves to be part of this symmetry just as much as the general covariance. Okay. So the structure that you get in this way is actually much richer than the structure of just the isomorphism group of one manifold. So you can compare it, for example, to the Poincare group. There are important consequences from that. One is, for example, that there is typical no natural, well-behaved kind of vacuum state. If you want to choose a vacuum state on all Lorentzian manifolds that behaves in the local covariant way, you typically can't do it. That's a result by Fusler and Verge under reasonable assumptions. Similarly, by combining locality and covariance together, you severely restrict renormalization ambiguities in perturbative theories. So this was a crucial input in extending things like the standard model and other perturbative quantum field theories to a generally covariant setting. If you don't impose locality and covariance together, there are way too many possibilities and you basically don't know what you're doing. Finally, in case any of you is familiar with algebraic quantum field theory, there is a similar remark to be made here. If I look at the typical theory, the non-trivial contents of the theory are not in the objects, so in the algebras that I'm looking at, but it's in the morphisms. And that is a very well-known fact also from algebraic quantum field theory. Local algebras are all isomorphic to each other, so knowing the algebra, basically you don't know anything. It's about how you embed these things into each other. And these morphisms for the theory can basically have the same rich structure as the localization category that you're using. So that's a much richer structure than you would actually have in Minkowski space. Okay. So let's now get really down to it and wonder, what do categories tell us about space-time? What is this notion of space-time? So considering again a functor from category of localization regions to the category of some physical systems, this phys category by itself would be enough to be a physical theory. It has all the systems and subsystems in there, so it should be enough to do physics. If you wonder, so where are the Lorentzian manifolds? They basically only enter in this category of localization regions, and to define the structure of that category. And what we then do is we use this functor A essentially to embed the structure of lock into the category phys. So we're imposing some structure on the theory phys that we have by using this functor from lock into phys. So the existence of this functor satisfying these axioms that we want to impose is a kind of condition that we can impose on the theory. So what I would like to propose as a matter of language is to say that the theory phys has a notion of space-time when it admits such a functor from the localization regions into the systems. And in that sense, space-time acts as an organizing principle. It imposes extra structure on the theory. It selects systems and subsystems. And I suppose that this would fit in very nicely with general epistemological views of what space-time is like. Perhaps going back to Kant or perhaps even older than that. So mathematically, what I would propose is to use the word space-time perhaps for the functor from this category of localization regions to some other category. So using the word space-time for the functor is perhaps a bit daring. It's really using it as something active that does something. If you don't like that, you might also use the word space-time at least for a category of localization regions, which is perhaps already closer to being a thing rather than something that does something. The main point I wanted to make here is that it might be better not to use the word space-time for a single Lorentzian manifold because it contains too much of a prejudice of what the universe looks like, and space-time is more than about just being a prejudice of what the entire universe should look like. So, and I want to get to a criticism that you might have saying, well, you want to move away from these Lorentzian manifolds, but fundamentally they're still there because they define the structure of this category lock. So you can't really do it without Lorentzian manifolds. You can try. So I'm sketching here an attempt to do that. This was not actually the essay. So in case you've read the essay and you want to learn something beyond that, this is a new idea. You can try to characterize the category lock fairly directly, hoping to get a unique characterization up to an equivalence in the categorical sense by saying, well, class of objects should certainly be non-empty. You want to do something. Every object should have a sub-object. There is no smallest Lorentzian manifold. These are basically open regions of space-time, so you can always shrink them. And when I'm saying sub-object here, so I'm thinking of something similar to subsets. It's a very kind of special kind of mapping between sets to be a subset. Points are not open Lorentzian manifolds, but you can perhaps recover points from this categorical structure by saying we should have suitable sequences satisfying certain properties, where you can basically think of taking Lorentzian manifolds and shrinking them towards a point and figuring out what kind of properties you want to impose there. And then continue by saying, well, the points that I get in some object should then carry a topology that I can recover from all the sub-objects, and from that point onwards you can try to recover all the properties that we normally impose on our Lorentzian manifolds. So what you then get is a whole list of properties that essentially should characterize the structure of this category lock. without starting with the Lorentzian manifolds as the most basic thing. So thinking about what a functor then does, you can actually say that these are properties that we require of theories or field theories living on space-time. There should not be the smallest system because I can always restrict it to smaller regions, things like that. So one thing that you can also say at this point is, suppose I want to go towards quantum gravity. I've now got a whole list of properties that basically encode what a classical space-time is. Which ones of these do I want to drop? Which ones are badly motivated? Which ones do I want to kick out to get a sort of generalized notion? Where the motivation for that idea is basically that the notion of systems and subsystems is perhaps more fundamental and should still persist also in quantum gravity theory. So this categorical point of view might actually still be valid even if Lorentzian manifolds are not there. So let me continue with a bit more of a view towards quantum gravity and first make the most obvious comment that we can now make after these discussions of space-time. The discussion then suggests that if I want to have a quantum gravity that explains space-time as an emergent notion, that means that my theory in some regime or in some limit should basically reduce to a locally covariant quantum field theory going from this category lock to some other category. The main point there is that it would not be sufficient to recover just a single Lorentzian manifold and diffeomorphism invariance there, because you would be missing the locality. You would get a very nice prejudice of what the universe might look like and general covariance for that, which is already a good result, but you're missing locality in some sense. Now, this is perhaps a bit obnoxious to make this comment because it's not easy to come up with quantum theories of gravity, and this comment is basically just saying we can read some of them out. So this is not very helpful to people who are actually doing something constructive, so it falls in the category, I don't have any solution, but I certainly admire the problem. I'm guilty of that on this occasion. Another idea towards quantum gravity is to say, can we take this categorical point of view and move the metric from the background to the dynamical side of things? You can actually start by looking at general relativity and see how you would do that there. So you might hope to get some functor that goes from some category of manifolds without a metric to some category that describes the physics. And I suppose that in this case, on the side of the physics, maybe you shouldn't be looking for observables, but maybe you should only look for partial observables, because the notion of local observables in general relativity is probably problematic. So this is not a very precise statement, but it mostly raises interesting questions. So a basic interesting question that you can ask is, suppose we're given any category that describes some physical theory, how do we know that it has a notion of space-time? Can we reconstruct it in some way? And another question that you can ask is, can we at least approximate a notion of space-time in this sense? Should we go to perhaps discrete space-time, non-commutative manifolds, things like that, to get an approximate functor between suitable categories or something like that? Or the approach I mentioned before, looking at the structural assumptions that you could have in such a category of manifolds, should we just look at that and just drop some of that to see if we can get a different category there to encode the structure of subsystems? Okay, so coming back to states and the idea that choosing a state specifies a different set of circumstances beyond choosing the system. You can basically say there are somehow different kinds of circumstances. So the system describes boundary conditions, external fields, physical operations you can perform, and a set of possible states, and then somehow the choice of state, in a sense, determines complete circumstances for the given system, so not for the entire universe. I'm not entirely happy with this distinction, because I'm not entirely happy with complete circumstances for the given system. So this is more of a question than a statement. what does that exactly mean? How should we think of that? In locally covariant quantum field theory, this is more or less given. It comes from the manifolds or the Lorentzian manifolds that we choose. But if you try to go towards quantum gravity, it's not so obvious what we're doing there. If it is actually still possible to choose in a coherent way between what circumstances belong to a choice of state and what circumstances belong to the choice of system. So that is perhaps an interesting question to look at, to see to what extent that might be possible. And you could then also wonder, can we characterize some kind of generalized notion of space-time to correspond exactly to a choice of system, essentially the way it does in locally covariant quantum field theory? I don't know what the answer to that question is. On top of that, I've listed here at the bottom the question, what conditions should we impose on the distinction between system and state? So in locally covariant quantum field theory, I've already mentioned this idea of local physical equivalence, that the choice of state should not contain any information that goes beyond the system that you're looking at. I don't know how that might be codified in a more general setting. So somehow the way states appear in here and what they would mean in quantum gravity is still a bit mysterious to me. Okay, so let me now come to my conclusions. I hope that I've convinced you that in locally covariant quantum field theory, these categories are used for a reason. They express the system's view of the world, which can then be used for a modal logic approach. They are used to avoid a kind of prejudice on what the universe might look like in a nice systematic way. And they refine the symmetry of general relativity from this isomorphism group to something that actually has a much richer structure. I hope I also convinced you that this allows us to characterize space-time in a slightly different way than say it's a Lorentzian manifold. You might say it's a functor from this category log into some category that is my physical theory. And I also hope very much that I've convinced you that this categorical language can actually help to formulate interesting conceptual and philosophical questions about what we really are trying to do when we do quantum field theory and curved spacetime, or also quantum gravity. And I hope that some of these questions should really fall within the realm of philosophy, where you might actually be able to come up with interesting ideas or statements that might actually also help to guide research in quantum gravity. Thank you very much.
Questions?
You have a question?
Yeah, one question. So, if I understand this correctly, like one part of this project is to define spacetime. You want to avoid questions about global questions about spacetime.
Yes.
And I wonder a little bit if that, kind of from a philosophical point of view, is a bit strange. It's kind of more of an epistemic, kind of epistemic versus logic. It might very well be that we have good reason to prefer one global vector to another, but wouldn't it still make sense to say, even though we can't, that we only have local data, there are many different ways spacetime can be beyond that. We want to model the space of possibilities there, even though we can be admit kind of our epistemic ignorance about which one is instantiated. So conceptually, I still think that the idea of the global spacetime should kind of make sense. Or am I completely missing where you're going with this and what the project is?
No, I think it's more or less correct what you're saying. So I'm not criticizing the idea that there might be a global spacetime that is actually suitable for describing much of the physics in the universe. However, when you're seriously thinking about going towards quantum gravity, where this notion of space-time as a manifold is actually probably a bad approximation at some point. And you're starting to wonder, so how should we get the space-time out? I think it is not so useful to think of space-time as being a manifold, and we're trying to get a manifold out. So this manifold is a mathematical model that we are using for a certain purpose. I would argue that we're using it for the purpose of selecting systems and subsystems in a nice, systematic way. I'm not perhaps fully clear on what kind of properties that we should require of this systematic selection of systems and subsystems. But the proposal is that this idea of systems and subsystems is more fundamental than the notion of space-time. It is something that should persist also in quantum gravity, that we can actually lock things out and say, we're now looking just at this part that I'm having here in the lab. And trying to recover this categorical notion of space-time in that sense might be more appropriate than trying to recover a single notion of a Lorentzian manifold on a global scale that describes the entire universe. So it might still be possible that in the end, when we've got our theory of quantum gravity, and we look at the right kind of limits and we model whatever we know, that we can find such a global notion of a Lorentzian manifold that works for the entire universe. That might still be perfectly possible. But whether it's the right idea to focus on that when you're trying to go to quantum gravity, that's more or less the issue that I'd like to think about and that I would like to criticize. I would like to say it might be more appropriate to use this categorical point of view there. Is that
so? I think this is very suggestive. I have a follow-up.
Just a second.
What?
Can you hear me?
Yes.
So they're drilling in the seminar room, and in this room they just started sandblasting outside. I think you might want to just turn our microphone off. We'll try and listen, but otherwise you're going to start getting a lot of noise coming through.
Okay.
And you guys ask questions and we'll listen as best we can. I'm sorry, it's a bit of a nightmare.
Okay. So I have a follow-up to that question. So if you look at the category phys, which tries to encode the structured relations between systems and subsystems, I think this is very suggestive, a very interesting thought of that could be pursued to perhaps create value in quantum gravity. Now, I would think that regardless of the specific physics, if we just think about the concept of what it means to be a system and a subsystem, that's a relation that partially orders physical systems, however exactly they're described. Some of these things will be asymmetrically standing in a subsystem, supersystem, or system relation. Some of them are not going to be so related. Surely you would want it to be transitive, so that if something is a subsystem of a supersystem, and that supersystem is a subsystem of a supersystem, then the subsystem should be a subsystem of the supersystem, something like that, right? Now, that's probably going to lead to, unless you make really wild assumptions, to there being some sort of maximal objects in that ordering. However, of course, these maximal objects, there may not be one single maximal object.
Yes.
But wouldn't that be weird if we would be in a situation like that? Shouldn't all, at the end of the day, be somehow ultimately a subsystem of the one and only universe? I guess that's the intuition I'm having here. Or do you want to keep it more general so that that's not necessarily the case?
Somehow I guess that my intuition is that this theory that we have describes a number of possible systems that could be the case, but not necessarily have to be the case. So the theories that we have usually also are able to describe systems that are not actually the case. And perhaps in some sense this is also one of the aspects that make physics a very powerful field of inquiry. It's not entirely clear to me that we should only look at theories that can only describe systems that are really actually happening out there exactly in that way. So it's not entirely obvious.
So, but you would want to leave open in your language, in your framework, to have to also be able to capture the situation where it isn't the case that there is one unique maximal object. In other words, where the subset relations do not terminate in one single universe, but because that's somehow an unkosher, what do you call it, prejudice?
I would have difficulty understanding how we could possibly figure out what that one system would be that is the entire universe.
Fair enough, but that's an epistemological problem, perhaps. It seems like conceptually, there should still be something like that.
So, so that, I mean, there is something there that I must admit I don't understand in how the word space-time is being used. So, one thing that you could be thinking about is that when we do physics, we do experiments and we like to be able to repeat them in order to get confirmation that we really are doing the right thing. So you can go into the lab and you can prepare your system the way you like, including some gravitational field, be it dynamical or not, and you got your big machine, you push one button sort of to prepare your system in the right way, you push another button to actually perform the measurement and you get a number out. Then you go for lunch, and after lunch you come back and you do the same thing again. The question is now, when I do that same thing again, do I really want to say I'm performing a measurement on the same system, or should I say I'm performing two different measurements, so that basically repeatability of measurements is completely out of it anyway, because I can only do things once. So to put the question another way, do I really want to use space-time, the Lorentzian manifold, to mean that every point in there corresponds uniquely to one event happening out there in the universe? Or in the system's point of view, it's perhaps more the case that I want to say, well, anything that looks locally like that can be identified with the system that I'm looking at, and then I can repeat measurements. So I've got the feeling that the question is somehow related to that distinction of how to use space-time. Do I really want to say space-time is the universe in a sense, and every event really happens once? Or do I want to say space-time is perhaps, well, I'm only looking at this particular system here, and I can recreate that several times in the lab and do my experiment over and over, and I can identify this event when I do the experiment the first time with the event when I'm doing it the second time. So there is...
so that you can sort of identify systems or classes of systems which are somehow the same system or perform the same experiment.
In some sense, the system's point of view seems to be a bit contradictory with the point of view that the space-time really describes the universe as it is, in a sense. I mean, I'm not a philosopher, and I guess I don't really fully understand what the situation is there and how best to resolve that. But,